This lecture is on implicit differentiation. So first, let's talk about functions or equations in explicit form and in implicit form. If you have the functions or equation y equals 1 over x, this equation is in the explicit form. It's because the variable y, the output y, is described using functions of the input x, right? And in other words, you just solve for y in terms of x. And then sometimes you can convert an equation from the explicit form into an implicit form. So by multiply x to both sides, you get x times y equals to 1. And this is an implicit form of this equation, right? And then you can find dy over dx, the derivative of y in terms of x using the power rule that we have learned earlier. Okay. How about when you are looking at this equations and your goal is to find dy over dx, which is the difference of y in terms of x at any point on this curve. You may wonder, can you convert this implicit form into an explicit form, which means solving for y? And the answer is no. So from this equation, you cannot explicitly solve for y. I mean, you can try, right? But it's not going to give you a precise or a very nice form that will put y on one side and the rest of x on the other side because of the nature of these equations. So then how can we find dy dx for this equation? Well, let's look at some example. So the first example, I want to find d over dx of 3x squared, right? It's just like if y equals 3x squared, then what is dy over dx? This question is about. And since you can see that this variable here and this variable here are the same, they agree with each other, right? That means you can just use one of the differentiation rules to find this derivative, and it will be 6x using the power rule. Go to the next example. I want to find d over dx of 3y squared. Okay. Now at this time, x and y, they are not the same variable. The variables here do not agree with each other. How can we find dy? How can we find these differentiations? So again, we still use a power rule, 6y, but then because the variables are not the same, that means we have to multiply to dy over dx. And you can think that, oh, this is very similar to chain rule when y is a variable of x, right? And y is a different functions in terms of x. And then you want to find dy, the derivative of the functions in terms of y, then you have to take the derivative of the functions in terms of y. Also, you need to multiply to y prime, which is dy dx. Okay. Then if we look at the next example here, right, you want to find d over dx of x squared plus 3y squared, right? Then I can use the sum rule, right? Which is d over dx of x squared plus d over dx of 3y squared. Since x and x are the same, I can just use a power rule, and x and y here are not the same. So then you have to use implicit differentiations, which you're gonna find the derivative of 3y squared in terms of y, which is 6y, and you have to multiply to dy over dx. Okay. Now go to the next example. You have a product of the two functions. That means you have to use a product rule. Okay. Using the product rules, I know that I have to find d over dx of x squared multiplied to y cubed plus d over dx of y cubed times x squared. Okay. Again, x and x here are the same. Then we can just use a power rule times y cubed. X and y are not the same. Then we have to use implicit differentiations. That means it's going to be 3y squared times dy dx. And then you multiply to x squared. All right. So this is how you find implicit differentiations, which is finding the differentiation or the derivative of y in terms of x for the implicit equations. Remember, if you don't have the same variables here, that means you need to use implicit differentiations. That means you can just find the derivative of the function in terms of y and then multiply to dy dx. Okay. Here's a guidelines for implicit differentiations, right? You differentiate both sides of the equation with respect to x if you're finding what is dy over dx. And you collect all the terms involving dy dx on the left side and move all other terms to the right side. Okay, so take all dy dx to one side and move everything else to the other side. You factor dy dx out of the left side, and then you solve for dy dx because the ultimate goal is solving for dy dx. Okay, let's look at an example here. Differentiating with respect to x to find dy dx. So you have an implicit differentiation, an implicit equations, right? An equation in the implicit form. And then you want to find for dy dx. And the first step is you take d over dx of both sides. Okay. Then again, you can use the sum and the difference rule to find the derivative of each of the term here. Okay. So x and x is the same. I can just use the power rule. X and y are different, then I have to use the implicit differentiations, right? 2y dy dx. X and y are different, then I have to use 5. Derivative 5y is 5 and times dy dx. And x squared, x and x is the same, so I can just use the power rule. And the derivative of -4 is 0. The difference of a constant is 0. Okay. And the next step is I want to move all the terms that has dy dx to the left side and everything else to the right side. So I keep these two terms on the left. And I move this and this term to the right. So 3x squared will be -3x squared, -2x will be +2x. Okay. All right. My next step is, again, the ultimate goal is to find dy dx. So I want to factor dy dx out. I got 2y minus 5 equals -3x squared plus 2x. And the final step is to just solve for dy over dx. equals negative 3x squared plus 2x divided by 2y minus 5. So this is my answer. So if I were given this implicit equation, I can find dy dx, which is the change of y, the instantaneous change of y in terms of x at any point, right, on the curve. Now look at the next example here. Again, I want to find d over dx of both sides. And again, I want to differentiate each of the terms in here, right? And x are the same, so I can just use the regular differentiation rule, which is cosine of x. X and y are not the same, then I have to use implicit differentiations. Plus 2, what is derivative of cosine should be sine of 2y, negative sine of 2y. And then you have to multiply 2, because it's 2y is not y, then you have to multiply 2 the derivative of the inner function, which is 2. And you have to multiply to dy over dx, because x and y are not the same. And on the right side, the derivative of a constant 1 should be 0. All right, does it make sense for you? So 2 is a 2 here. So I want to explain it a little bit here. 2, I just carried out, is a constant multiple rule, right? And the derivative of sine of 2y should be sine negative sine of 2y. Using the chain rule, multiply to the derivative of the inner function, which is 2y, 2 here. And at the end of this differentiation, you need to multiply to dy dx, because x and y are not the same. Okay. So the next step is to keep dy dx on one side and move everything else to the other side. So dy dx attached to this whole term. So I have to keep the whole terms here. Sine 2y. So I multiply 2 to 2, I get 4. Negative dy dx equals 2. I bring this to the other side, negative cosine of x. Okay. Then the last step is I just want to solve for dy dx. Negative and negative would be positive, so cosine of x divided by 4 sine of 2y is my answer. All right. Now the next exercise is if you're given in implicit equations, right? An equation in the implicit form, and you want to find the slope of the tangent line to the graph of these equations at the point C. Again, in order to find the slope of the tangent line, you need to find dy dx. Okay, and then at the point C, so the slope is just the derivative at the point C, then find dy dx when at the points 3 and 1. Okay, and then you can find the slope by evaluating the dy dx at 3, 1. Okay, let's try that. So you're given this equations here, and it is an implicit implicit equations, right? Is an implicit form that you have to, in order to find dy dx, you have to differentiate both sides, right? Taking d over dx both sides. What happened on the left? On the left here, as you see that you have 3x squared plus y squared and square. So then you have to think of this as u, right? Is you taking this differentiations using chain rule. And using chain rule, you see that this is the inner function's u, and the outer function is u squared. Right, u equals to x squared plus y squared. And the f of u, right, is u squared, 3u squared. See, x squared plus y squared. Okay, and then f of u is 3u squared. Then the differentiations here will be equals to f prime of u, which is 6u squared, 6u. If you use the power rule, you get 6u, right? Multiply to the differentiations of u, which is x squared plus y squared. Using chain rule, okay? What about, well, let's try to finish the left side and then we go to the right side. So we know u, sec u is just 6 times x squared plus y squared. And then multiply to this differentiations. And I can differentiate this, right, separately. So x and x are the same, then it's gonna be just 2x using power rule. And x and y are not the same, then you have to use implicit differentiations by taking the derivative of y squared, which is 2y, and then you have to multiply to dy over dx. All right. Now, the next step is, since you have dy over dx in the parentheses, you want to, because at the end of the problem, you need to pull the dy dx out, and you want to combine all the dy dx term together. So that's why I want to do it now, right? I want to distribute 6x squared y squared into these two terms. So you get 6 times 2 is 12x squared plus y squared plus 12y x squared plus y squared dy dx. Okay, so now I have my dy dx terms separately. It can be done for the left side now. Now go to the right side. The right side is when you need to find d over dx of 100 times x times y. So what is going to be? It's going to be, well, I can pull the 100 out, right? And then you have, this is a product, so you have to use a product rule. So the product rule say you take the derivative of the first functions, multiply to the second functions, and plus the derivative of the second functions, and then you multiply to the first functions. So the derivative of x is just 1. You have 100. 1 times y is 1. d over dx of y, right? The derivative of y is 1 times dy over dx times x. Okay. Here. So this is here, and this is actually it's 1 times y, but I just skip it. All right. Then the next step is, again, because I want to pull the dy over dx out, then I would like to distribute this in. So I have 100y plus 100x dy over dx. All right, now is a step when I can pull the dy over dx terms to one side and everything else to the other side. So I keep these terms here. I put 12y x squared plus y squared dy over dx. And I bring this term over, minus 100x dy over dx is equals to 100y. And I bring these terms over to the right, so 12x, x squared plus y squared. Okay. Again, the next step is I want to factor the dy over dx out. I have 12y x squared plus y squared minus 100x equals to 100y minus 12x x squared plus y squared. Then the last step is just solving for dy over dx equals to 100y minus 12x x squared plus y squared over 12y x squared plus y squared minus 100x. All right, so I found dy over dx. Then the next step is I need to evaluate dy over dx at c at the point 3, 1. The next step is evaluate dy over dx at 3, 1. That means I plug 3 into the x's and 1 into the y's. Okay, so I have 100y is 1, right? Minus 12, 3 squared plus 1 squared divided by 12 y, which is 1, times 3 squared plus 1 squared minus 100 times 3. Right, 3, 1 is a point. All right, now I just need to evaluate this derivative dy over dx at 3, 1. And the answer for this calculations is 13 over 9. So we found that the derivative dy over dx at x equals 3, y equals 1 is 13 over 9. So this actually the slope. So then the slope of the tangent line to the curve, to this curve at 3, 1, right, is 13 over 9. So you found the slope of the tangent line, then actually you can find the tangent line, this tangent line. So the tangent line to this curve at the point 3, 1, right, is y using the point slope form, y minus 1 equals to 13 over 9 x minus 3, right? This is the tangent line. So you found the slope, you know the point, then you can use a point slope form to find the tangent line. All right, let's look at the graph, right, of this curve. So this is the graph of the curve 3x squared plus y squared equals to 100 times xy. And I plot the point x equals 3, y equals 1 is right here. And I found the tangent line. The tangent line was y minus 1, right? Equals to 13 over 9 times x minus 3. And as you can see that this green line here is actually the tangent line to this curve and the point 3, 1. And we found the line, right, tangent line using implicit differentiations. And again, look at this curve. It's not a function because it's violate the vertical test. So once you find, you know how to find dy dx of any curve, right? Using implicit differentiation, then if you want to find the second derivative of y in terms of x, you can just find the first derivative and then you find the second derivative. This is an example of the second derivative implicitly. So first we need to find dy over dx, right? And then finding d squared y over dx squared by finding the derivative of the dy over dx. So in order to find dy dx, again, we just need to differentiate with respect to x of both sides. And then if you look at these differentiations, you have a products, right? And the two terms. And so then you just need to find the differentiations of this term and then minus the differentiations of this term. And again, the differentiations of a constant is 0, okay? And then you can look at, so you have a product, then you have to use product rule here. The product rule say that you can take the derivative of the first functions, multiply to the second functions, plus the derivative d over dx of the second functions, and then multiply to the first functions, minus the derivative of 4x, right? D over dx of 4x is just gonna be 4, equals to 0. So then, again, x and x are the same. We would just use the power rule. So it's gonna be 2x times y squared, right? Plus x and y are not the same. Then we have to use implicit differentiation, which is gonna be 2y times dy over dx. And times x squared minus 4 equals to 0. Okay, again, the goal is finding dy dx. So then you want to keep this term here, move every terms, other terms to the other side. So you would have 2y times, I move x here, dy over dx equals to, I move the 4 over there, which is 4, and I move this to the left side, which is to the right side, which is negative 2xy squared. Then again, dy over dx equals to 4 minus 2xy squared divided by 2yx squared. All right, so I found dy dx. Now the next thing is I need to find d squared y over dx squared. That means I just have to differentiate this one more time, right? So I say I want to take d over dx, right, of this dy over dx, which is the same as d over dx of 4 minus 2xy squared divided by 2yx squared. Okay, so I differentiate dy over dx to have the second derivative. And again, I'm gonna do it again, right? So if I look, now that I look at this new problem here, this new differentiations here, I have a quotient, so I have to use a quotient rule. So using quotient rule, I would have this here will be equals to, I take the derivative of the top, multiply to the bottom, minus the derivative of the bottom. And I multiply to the top by the top functions. Okay. take everything divided by the bottom functions square. Okay. So that's a quotient rule, how to find this differentiation. And then one more time, right? I'm gonna use different rules to find this derivative and to find this derivative. Okay. So this derivative here is, so you can see that you find the derivative of 4 and you find the derivative of 2xy squared. And the derivative for is, of course, 0. And the derivative of negative 2xy squared is a product. So then you have to use the product rule. So let's do this piece by piece. And then we're gonna plug everything in together later. So my point is I wanna find this derivative separately. And it's gonna be equals to, so the derivative for is 0, right? Minus 2 times, using the product rules, it's gonna be d over dx of x times y squared plus d over dx of y squared times x. It's gonna give you d over dx of x will be just 1. So negative 2, 1 times y squared, it's just y squared. Dx over dy, x and y are not the same, so then you have to use implicit differentiation. So it's gonna be 2y times dy over dx, right? And then you multiply by x. All right, so that's the first term, right? The first differentiations. How about this differentiations? It's very similar, right? But we just have to do it here. So you have d over dx of 2y x squared. Using the product rules, it's going to be, and constant multiple rules, it's going to be 2 times d over dx of y times x squared plus d over dx of x squared times y. Okay, that's going to give you 2. X and y are not the same, so you have to find the derivative of y. It is just 1 times dy dx. 1 times dy dx plus the derivative of x squared, it is 2x times y. So you found these 2 pieces and you wanted to plug these 2 pieces into its own place, right? So I want to plug it here and I have this here. I want to plug it back here. Okay, to finish my problem. But the thing is, in this differentiation, you still have dy over dx and you still have dy over dx here. What does it mean? That means when you plug it back here, you still have dy over dx. But then the goal is, again, the goal is finding d over dx of dy over dx, okay? And then you should have dy over dx here. Then that means you need to replace dy over dx by an expressions in terms of x and y, not another derivative. And then we know that, oh, we found what is dy dx in terms of x and y is actually the first derivative. So the next things I want to do is I want to actually replace dy over dx by this term right here. Okay. So I would have put in here the negative 2y squared plus 2y, and dy over dx is 4 minus 2xy squared. Over 2yx squared multiplied by x. Okay, and again, this differentiation, I have 2 dy over dx is 4 minus 2xy squared over 2yx squared plus 2xy. Okay, now is a good time when I can plug this into here, right? And then this into this one to finish my problem. So that's let's rewrite this. At this point, I have negative 2y squared plus. So I'm going to bring this up here and this up here. And if we look at this expressions here, we can try to simplify x, right? Because this form here, you have 2 times y dy dx times x, then you can simplify this x to one of the x terms here. And then you can simplify y with this y here, and then 2 with this 2 here. So what left over is just 4 minus 2x y squared divided by x as the result. So this is going to be just negative 2y squared plus 4 minus 2xy squared divided by x as the result of the simplifications. Look at these terms here. Doesn't seem like we can cancel anything out, right? So we'll just keep it like that. And then we put this term, this expressions here into this differentiations, and this expressions here into this differentiations to find the second derivative, which is up here. Okay, so I plug the differentiations multiply to 2y squared, yx squared minus the negative 2 multiply to 4 minus 2xy squared. It's a long expressions. Let's see if we can simplify any terms. So we can try to distribute all of this in to see what happens. Okay, I want to look at the difference. So it's still dy squared dx squared equals to, I multiply this here, right? And then negative 2y squared times here, you get to have negative 4y cubed x squared. All right, and then I multiply this in here and then in here to get negative 4, right? Negative 4yx squared times 4 minus xy squared divided by x. Okay, so first term. The second terms, I will have this, I will multiply this into here, okay, and then this into here. So you get 8 minus 8, 4 minus xy squared divided by 2yx squared. Okay, so that's one term. And then I can multiply to here, and then I multiply to here to get also negative 8 so I multiply to these terms first. So I get negative 2, 4 minus xy squared divided by 2yx squared. I'm running out of space here. And multiply to 2xy squared, right? 2xy squared. Okay. So that's just the first term here, and I need to multiply to this term to here and this term to here. Okay. So this here, and then the next term will be -2 times 2xy times 4 is -2 to 4, 16. I get -16 times xy. And I have negative and negative, which is positive. So then I have to multiply with here, -2, 2, 4 is going to be 8 plus 8 xy and times 2xy squared. Okay. And then everything, remember, divided by 4y squared and x to the 4th. This is the denominator. Here, here, here. Let's see what else we can cancel. So we can, oh, look at here. X and X can go, right? That's the first thing. And here we have X and X here, Y and Y here. Okay. And you have 2 and 2 can go as well. Okay. So the next thing we want to do is -4y cubed x squared minus 4y x, 4 minus xy squared minus 8, 4 minus xy squared over 2yx squared minus 2, 4 minus xy squared over xy minus 16xy plus 8. If I combine this, it's going to have x squared y cubed. Again, everything over 4y 4x to the 4 y cubed, square x to the 4th. It doesn't look very nice. Well, then maybe we can just stop here as this doesn't go any further. I guess we can cancel this term and this term, right? Is there any xy term that we can cancel out? And we have this square, and then this, if you multiply this together, you can also simplify it. You can simplify a little bit further, but I'm running out of space here. So I guess we can stop here for this moment, right? So then this is d squared y of the x squared. And again, simplifications can be further do, but we just stop here for the sake of running out of space. So that's the idea. So you find the derivative using implicit differentiations, and you find the derivative again. And at the end, you can simplify some of the terms just to make it nicer. All right, so this lecture again is on the implicit differentiations that helps you find the derivative of y in terms of x for equations that in the implicit form.